Yeah. So, hi everyone. I'm Haoting. I'm from Professor Haoting Xu group, and today I'm going to talk about our recent paper, which is posted on arXiv yesterday, and it's called "Manipulating Majorana zero modes in the spin-1 level." Okay. So first, let me give you an introduction. So this work is about the topological quantum computation. So the idea of the topological quantum computation is that there's a decoherence issue in the quantum computing, which people consider a very serious challenges of realizing the quantum computing. So the topological quantum computation solves this problem an elegant way by using fractionalized excitations in the many-body system, so that the quantum information is stored and manipulated using the fractionalized excitations, so that they become more stable under the environments. And one of the important building blocks is the fractionalized excitations. They encode non-abelian statistics, so that you can so that's a building block of the topological qubits and the topological bits. But then people think about what are the platforms to realize this topological quantum computing. So one of the platform is Cairo P plus IP with superconductor. So this is a theoretical model with the superconductor order parameter have this Px plus IPy dependence. And in this model, people have found that if you consider a vortex of the superconducting order parameter, then you will discover a localized quantiparticle. And this localized quantiparticle is described by a Majorana fermion. And this Majorana fermion, different from the ordinary fermion, they have a gamma dagger equals to gamma, means that their antiparticle is its own. So that there only exists one degree of freedom. And you have proved that when two vortices carry the Majorana fermion, when they exchange, the Majorana fermion will occur at a high bit shape. Like you have a gamma 1, gamma 2 in the P plus IP superconductor, and if you exchange them, then gamma 1 becomes gamma 2, and gamma 2 becomes minus. So this will lead to kind of the non-abelian statistics that if you have n vortices carry n Majorana fermions, then you exchange 1, 2, 2, 3, 3, 1, then you have a non-abelian relation. Also, there are some alternative platforms, which is called the Kitaev spin model. And Kitaev spin model is it has a bond-dependent Ising interactions. So this X bound means these two is a spin half. So there is a spin half on each side, and the X bound means the interaction is a sigma x, SX, and a Y bound and Z bound. So if you consider such a model with a magnetic field, then the model will appear a gap, and there will be Majorana fermions and Z2 vortices. Similarly, the location of Z2 vortices and Majorana fermions are the same. So they also obey such a non-abelian statistics. Okay, so this is what we are going to find, and there are already some candidate materials like the iridice, lithium chlorine, and qubits, etc. So parallel to the search for 2D platforms to realize the topological quantum computing, research also focus on the 1D topological systems to see whether 1D topological systems can realize the topological quantum computing. So one of the most simplest model is called the Kitaev chain. So as a Kitaev chain, I don't know why the rest is here. So each J site carries so these AJ diagram AJ are annihilation and accretion operators for electron at the given site. So that's the Kitaev chain introduce so these are the Hawking terms, and this is the superconducting parent term, and then there's a chemical potential. So this model is exactly solvable, and here there should be a red circle. So if you consider some special parameter sets, for example, when W equals to delta, when the delta, the superconductor parent is bigger than the chemical potential, this Kitaev chain is within the topological base. That means this red circle, these two red dots represent two Majorana fermions, and they collectively represent one electron size. So that you can see the Majorana fermion of different electron size, they pair together, leaving isolated Majorana mode on the end. So this is called topological phase. And when the chemical potential is large, chemical potential means chemical potential coupled with the number of the electron given site, then you can these red dots within one electron so that it becomes a non-topological phase. So people have explored the possibilities of these models, and people present, wow, maybe we can move them around the fermion around the 1D P-wave superconductor. So theoretical protocols have been proposed. One may have some all these are electro voltage. So one can apply the electro voltage to change the parameter, the chemical potential. So suppose we change the electric voltage, then this part become non-topological and this part is topological, so that the edge Majorana mode can be moved from the boundary of the topological phase to the intersection of non-topological and topological phase. We also investigated the minimum of the braiding, which is the braiding rule is one of the block of the nonlinear statistics that's using T junctions. So people have a gamma 1, gamma 2 pair. So this is topological phase and this is non-topological phase. Then this gamma 1, gamma 2 can be exchanged by this process. So all these researches, and also because if you want to explore nonlinear statistics, you will have a lot of these Majorana fermions, so that you can so that they have a nonlinear relation. So the researchers have studied that if you have all these P-wave superconducting from your wire network, then you can exchange gamma 1, gamma 2, gamma 2, gamma 3, gamma 2, gamma 1, etc. to have a nonlinear statistics. So all these researchers have explored the possibility of realizing the CQIQC using 1D statistics. So motivated by this research, we are going to look at the Kitaev ladder, which is a one-dimensional version of the Kitaev spin model. So we want to know whether there's a boundary Majorana mode and how we can manipulate them in these spin systems. Okay, so the Kitaev ladder is, as you see, we have X bound, Y bound, and Z bound, and the Hamiltonian is the interaction between the spin halves. And actually, these models can be diagonalized by Jordan-Wigner transformation by writing the sigma plus the raising operator of the spin as the creation operator of the fermion, and times the S-string is the string operator. And this string operator, and the usually Jordan-Wigner transformation, as you know, is going to solve the spin system in 1D. But here we have another chain, so now we have two chains. How can the Jordan-Wigner transformation solve this two chains spin model? Is that because of this Z bound, because we have this bound dependence X, Y, and Z. So when you consider the Z bound will become a local object instead of a non-local object. So suppose so we define these Majorana operators so that for each site, for example, JA, the FJA is decomposed to two Majorana operators, gamma and gamma theta, and for each site JB, it's similar. So if we define these Majorana operators, then we can write the spin problem by this local fermion problem. So this local fermion problem involves the gamma hopping on the first chain, gamma hopping on the second chain, and then we have a KZ interaction involving gamma JA-JB, gamma GB, and gamma theta JA and gamma theta. And okay, so I forgot to put the definition. So one can observe that this quantity, gamma theta, this we call it DJ, defined on each vertical bound. So on each vertical bound, we define gamma theta as DJ, and we observe that this DJ commutes with the Hamiltonian and with each other. So this means that the Hamiltonian can be diagonalized in different DJ settings. So there's a theorem by Lee, and Lee's theorem said the ground state resides in the pi flat state. So pi flat means that DJ times DJ plus 1 is -1, means that you need to choose the DJ sector as +1, -1, +1, -1, etc. To reach the ground state. But that would means two options, because you only have this constraint dj plus 1 equals to minus 1. You can have plus 1 minus 1 plus 1 minus 1 and also minus 1 plus 1 minus 1 plus 1. So if dj and minus dj sectors have the same spectrum, exactly the same gamma spectrum, and this spectrum is related through a local unit transformation of quantity. So here the problem is the dj plus 1 minus 1 minus 1 plus 1 are degenerate. So if we consider an arbitrary superposition of the two degenerate states, then the Majorana mode may annihilate or create or form a complex fermions. So how do we detect the single Majorana mode? So to detect the single Majorana mode, one needs to selectively choose one of the DJ sectors. So here we propose that the DJ sectors can be selected by the projective measurement of the quantum states, and the projective measurement is equivalent to apply the projector, one of the projector on the quantum state to select the desired DJ sectors. And one only need to consider the, for example, type 1 is on the first bound, is on the first vertical bound. Then one after applying this operator, one selectively choose one of the two states. So that one fix the DJ sectors. And note that because this DJ sectors is not highly non-local operators as written here. So once the DJ flux is fixed, then one can possibly change the DJ flux. So the operator that can change DJ flux is a local spin operator. The local spin operator, this is the XX operation on a Y bound. So suppose we have a Y bound, then you apply XX operators on the quantum state, then you can show that you effectively change the DJ actually change the adjacent DJ operator. So if you apply XX operators on this Y bound, you will flip the sign of DJ of these two bounds. Okay, so with the projective measurements and the local spin operators, one can reach any of the DJ sectors. Okay, so after understanding the Z2 flux, then we explore the phase diagrams by when we fix the DJ. So when we fix the DJ, we have the 4-band dispersion because one unit cell contains 4 sublattices. And there will be 4-band. I denote that the EK plus minus with a pi because I'm obtaining the phase diagram of the pi flux. And the dispersion is looking like this. And here is the phase diagram. And the gap closes at these transition lines. And it divided the phase diagram into 3 phases, which we denote as the TX, NT, and TY phase. So how to understand these topological phases is by going through the extreme limits of your parameter. So for example, in the TX, we can consider when TX is very, very large, what is Majorana like Majorana state. So when TX is very large, you can see the X bound is very, very large. Then we have a edge Majorana mode here and also an edge Majorana mode here. So this is we call topological phase. And also one can compute the Chern number of these bands, and you can see and then one will obtain the topological phase will have a non-zero Chern number. And for the non-topological phase, one can consider limits when KZ is very large. So when KZ is very large, then the Majorana fermion on each bound is coupled together, then leaving no atom. So after understanding of the pi flux, there's a because there we can control the DJ, and there's a possibility of different DJ sectors. We also explore the phase diagram of the zero flux. So the zero flux is DJ is all equal to +1. So at this case, one can also diagonalize the Hamiltonian and obtain the band dispersion, and one can also obtain the phase diagram. One can see the same phase TX, TY, and the non-topological phase, but they have a different transition lines. So this is interesting because when you consider parameter x to LTZ, for example, at this region, then you can see at the pi flux, this region is non-topological, but in the zero flux, this region becomes topological. So this gives us a tool to manipulate the topological nature of the system by tuning the DJ sectors. Okay. Then after considering the extreme parameter sets in extreme limits, we also want to know how to find Majorana zero modes exact form of Majorana dual gamma A, gamma B at general at some arbitrary CQIQC. So the technique for understanding this is by writing the system in the Heisenberg picture. Heisenberg picture means that your operator is time dependent and your state is time independent. So in this case, one can using the Heisenberg equation to find. So we suppose gamma A is some linear superposition of gamma JA and gamma B is a linear superposition of gamma JB. Then one can find the Heisenberg equation of motion, and because we are going to find the Majorana zero mode, because they are free degree of freedom at the edge, so they are zero modes, have zero energy. Then we are looking at the omega equals to 0. And by using some anti-communication relations, one obtain the relations of these coefficients of the linear superposition. Then one can start with an arbitrary boundary condition. For example, one start with alpha 1, beta 1, and then obtain all the alpha j and beta j. And then finally, we also normalize the gamma A and gamma B for they to satisfy the relation of the Majorana fermion. Okay, so to get an insight what's happening in the topological case, we diagonalize the Majorana Haoting problem by fixed DJ sectors. So that's the Hamiltonian will become a matrix interacting with the Majorana Haoting, and we just diagonalize the Hughes matrix, and we choose numerically n equals to 1000, and here is the coefficients. Also can be understood that the probability of this locating isolated Majorana, which is alpha j squared and beta j squared, we can see a clearly exponentially decay atom in the topological phase. And here we choose the DJ within the pi flux, and the Kx is very large compared to Q1. Also, despite the numerical simulation, actually these relations between the coefficients are exactly solvable, and one can exactly solve them to see where the exponential decay or growth happen by these conditions, and one can also define the topological invariant by whether there's a topological decay of the probability of locating Majorana fermion, and one can find exactly the same phase diagram as the band dispersion. Okay. So now what's interesting is for a given parameter set. So for a given fixed parameter, Kx, for example, equals to 1, Kx divided by 1 to 5, so y equals Qi divided by k to 1. Then for fixed parameter, if we have a different flux sectors, high flux on the left, which is supposed to be empty phase, and zero flux on the right, supposed to be a TLS phase, can we have a Majorana mode at the intersection of the NT phase and the TS phase? The answer is yes. And here is another numerical simulation of n equals to 1000, and one can see there's a very large probability at the intersection, and also can be conceptualized when you consider the zero limit. There's a red Majorana here, and you can see a large Majorana at the boundary as well. So this motivates us to possibly manipulate and fuse these Majorana fermions in these ladders. So one can begin by preparing the TX or TY phase for your spin model have these for the TS to TC have these conditions. Then you have a TX or TY phase, and with two edge Majorana. What time? What time is it? Okay, yeah. So TX and TY phase, then we can directly move this gamma A and then fuse them to a vacuum sector or fermion sector by changing the DJ flux. Okay, and we also discussed the engineering of the potential engineering of the ladder, which could be realizing our 2D material. But so these red atoms are D5 configuration that have effectively spin half, and we have other spin degree. We can choose other atoms as D6 and other spin degree for them is frozen, and one perhaps needs some insulating barrier to prevent the charge transfer. So motivated by such potential engineering, we consider such model because this KZ bond around the like across the hexagon is weaker than the KZ. So we also consider whether if this KZ bond is replaced by the KZ prime, what will happen? It turns out that the phase diagram shrink by distance of square root of KZ prime divided by KZ. This means if you have a KZ prime divided by KZ is 0.01, you still have a 0.1 width of this regional integers. Okay, and also this is the 0 plus phase diagram. Okay, and so, but there are some challenges because when you introduce such engineering, there could be other interactions, other symmetry logic interactions that from and Heisenberg interaction they could not be removed. And also, some researchers have discussed with the Kitaev interaction plus the Heisenberg gamma interaction, and with the small Heisenberg gamma interaction, they are within the same phase. But there is a question of how to identify the Majorana fermion in the presence of other interactions. And also, because we are going to add some insulating barrier to prevent the charge transfer, the insulating barrier may have some D shape of this perfect octahedral structure. Okay, so here are summary. We motivated by this research, we explored the Majorana fermion, or in the Kitaev spin ladder, we obtained different phase diagram for different flux sectors. We identified the Majorana fermion. We explore how to fuse the Majorana fermion and move the Majorana fermion. And we also discussed the materialization and the challenges. Thank you. Yeah.
You go back to the slide on the P-wave superconductor because you showed braiding of Majorana particles, and I kind of didn't get why you mentioned it here.
Yeah, because it's as these research are possibility of realizing the TQC. So one of the building blocks of TQC is you braid the two Majorana modes, and there will be a non-abelian braiding. Using this 1D system, the 1D system from aware, there could be a possibility of braiding like within the T functions. And when you form a network, then you could have some braiding, and then you could have some non-abelian.
So could you, because maybe I just don't understand, what is this T structure here?
Yeah, so
maybe I just don't get it. Yeah.
Yeah, so the T structures are like two pieces of P-wave superconductor. There are some complicated connection between here, but you can just consider it as two pieces of P-wave superconductor. And suppose that the topological nature of the P-wave superconductor can be controlled by modifying the chemical connection. So that this phase is non-topological and this phase is topological. So if you have a two Majorana fermion and then you can change the topological piece of this part by changing the chemical potential, and then this Majorana mode is able to move.
So you perform the switching of Majorana modes by changing the sector of where this logical unknown.
Yeah. And then the similar to the P plus IP superconductor, it will have a high phase. Okay.
Yeah. What did you mean by the like gamma and Heisenberg interactions that you mentioned? Like, what do they correspond to in a physical system?
Yeah. So in the physical system, potential physical system, these are pseudospins. So the pseudospins are made by the spin-orbit coupling. So angular momentum coupled with spins, and when you form such a crystal structure, means that each atom is living within an octahedral environment. Then there are some orbitals of living on spin orbital living on these atoms. And if you ignore all the components that are zero, what will remain is the Kitaev and the Kitaev gamma interaction and Heisenberg. So they are the non-zero elements of orbital.
Okay.
DJ terms. Physically, what do they mean? I understood the DJ.
Yeah.
Minus one.
Yeah. So for one spin site is decomposed to two Majorana, gamma and gamma theta. And if we perform this math, then we can see the Z bond will become gamma A, gamma B, and with gamma theta is equivalent. And we observe that this quantity are commute with the Hamiltonian and also commute with each other. So we define this quantity as DJ.
But if I go back to the spin, Pauline spins,
Yeah.
What does it mean in terms of those?
Yeah, this meaning terms is a very non-local term. For example, if you are looking at a DJ of D2, then you have a D2 x D2x, then you have a sigma z of all these you on the side. So it's a highly non-local object.
Okay. Thank you very much for both of you. Yes,